Thank you, Ellie. Okay, everyone. Welcome to our first science talk of the evening. And let me introduce our speaker for this evening, Dr. Nierenberg. She completed a PhD at UC Santa Barbara and has previously held postdoctoral positions at Ohio State, UC Irvine, and was a NASA postdoctoral fellow at JPL. Dr. Nierenberg is currently a professor of physics at UC Merced, where her research focuses on star formation in small galaxies and using gravity to create dark matter. Tonight, she'll be talking to us about searching for dark matter with James Webb Space Telescope and the UC's own Keck Observatory.
Thanks so much. So I'll just confess my sins. I underestimated how carsick I would get driving up. It took me a little, I just got here, so I'm a little frazzled, but I'm so excited to be here. And as an astronomer, it's so amazing to see how many people made the trip up here for this opportunity to visit this beautiful observatory and look at the stars and listen to some music together. This is a frequently asked question I get, so there it is. It's actually pretty much a straight shot east of here. It's a little less twisty of a road than the road up from San Jose. And I know that because when I was at Santa Barbara, I came up here multiple weeks to observe as a graduate student. And I don't think I've been back here since about 2014. So it's cool for me too. But here we are in the Central Valley, and we're the newest university in the University of California system, founded in 2005. Okay, you guys know this one. So we have about 9,000 undergrads right now. It's still quite a small campus, but we're looking to grow. We have about 600 doctoral students, about 50 in the physics PhD program, which when I look at that is actually a sizable fraction of the number of doctoral students. And as you also know, I like to highlight that we're just 90 minutes to Yosemite National Park. Okay, so now to science. So I think it's really easy, and when you read popular science articles, you get the impression that we know all there is to know about science. We're really excited to tell you about all the things we know about, right? And here's a nice picture. We know about matter, right? Matter is made of atoms. And can everyone hear me okay, by the way? Is the amplification okay? Okay. Atoms are made up of nuclei and electrons, and then we can break it down further, protons, neutrons, and even quarks, right? We can see those in things like the Large Hadron Collider. We have this beautiful picture of what the world around us is made of, except it's really sad it only makes up 4% of the universe. So 74% of the universe is dark energy, 21% dark matter, 4% normal matter, which is a very, obviously the normal matter here is not the 4%. I think one thing I'd like to just say for those of you who've ever wondered how you put energy here on the same pie chart as something like matter, maybe that's something you've asked yourself. And this is like a little tidbit for the super science people who want to know, but you can just use something like E equals mc squared. Energy equals the mass times the speed of light squared, and that will give you an equivalent energy for a mass. So if we want to put everything on the same pie chart here, we're just doing that kind of a calculation, just in case you ever wondered. And so I'm talking about this 21%. I'm not trying to tackle this one. I'm going to tell you about the 21%, the dark matter, what we know about it. And I think this is a really important part. Like, why do we think this exists? Why do we think 21% of the mass energy in of the energy density of the universe is not those nice story I told you about with the quarks and everything? So first, the first thing to remember is that gravity is a force. It pulls things toward each other. Now, this is not a scientific figure, which you can mostly tell because of the ratio of the size of the moon to the Earth. But if you have more pull, more gravitational force, you have a higher orbital speed. So if you look at the planets going around the sun, you can see the sun pulling on the planets. That's that gravitational pull. And what happens is we see a lot more gravitational pull in the galaxy than we expect from just gravity. So here's a figure that we can use to plot this quantitatively. So here, if we look at this galaxy here orbiting around, the stars are moving with a velocity here, measured in kilometers per second. And on this axis here, we have a distance. So as I get further away, the velocity of the stars that I measure going around this galaxy is going higher and higher and higher. If I just do my calculation on the gravitational pull I expect from those stars in that galaxy, I really would have expected it to fall off like this, based on what I believe I know about the mass of stars, which I can measure very accurately by looking at stars, like for instance our own sun and then other stars in our galaxy. So if I just do that pull calculation, I expect this dashed line here, the velocity should fall. Instead, what I see is that the velocity is rising and rising. This is fundamentally one of the most fundamental reasons we think that dark matter is real. And here's a nice graphic that hopefully I can cause to play for you. Okay, so this is what a galaxy would look like without dark matter. So here, these stars on the outside are orbiting around the center of the galaxy more slowly than the stars in the center are orbiting around. That's because there's less gravitational pull as you get further from the main body of stars, less force, and then a lower velocity. That's what you would expect to see if you looked at a galaxy without dark matter. What we actually see is this picture here. This is a flat rotation curve in this case, as opposed to the totally rising one like I just showed you. But you can see these stars moving much more quickly around the edge of this galaxy than these stars are in the no dark matter case. That's that difference in the amount of pull. And hopefully I can go to the next slide. Okay, so it's not just in galaxies that we see this phenomenon where you need extra gravitational force to explain. So not just stars and galaxies, but also if we look at the motion of galaxies orbiting around each other. So each of these yellow spots here is a galaxy in a group of galaxies really far away from us. And we can look at how fast they're moving in this huge, enormous cosmic group of galaxies. And their velocities also cannot be explained without the addition of some dark matter. And then there's also this cosmic microwave background. If we do some calculations of how the light is correlated with each other, this is a way of looking at how correlated the different peaks are in this light distribution. And this is all the light coming from early on in the beginning part of the universe. This is pretty technical. But the point is even that cosmic microwave background, that signal coming from early in the history of the universe cannot be explained without adding dark matter. So these are some really different size scales and time scales that are all being explained really well if we have some dark matter, some extra particle. And so I'm going to go ahead and show you the cartoon of what we think we know about dark matter that would explain all the observations I just talked about. So it would have to be a new kind of particle. For a variety of theoretical reasons and observational reasons, it cannot be one of those particles I described in the standard model of physics. Oops, sorry. It does not interact significantly with ordinary matter except with gravity. If it interacted, for instance, with light, we would see that in some different ways. One of them would be in the cosmic microwave background signal. We would also maybe just be able to see it by absorption or reflection or some kind of interaction with ordinary matter. So we can place limits on because we don't see it. It also can't interact significantly with itself. So it can't be like an electron with a proton. It can't be interacting strongly with itself. That would have some effects on how the structure would form. And I already said this, it doesn't interact with light. And we can also place limits on, it must make up about 85% of the matter. So if you think about all those observations I just described, and you add in some extra theoretical physics, you get these sort of facts that we think we know. And actually, I mean, this is a pretty good fact to know about something that you can't detect at all, right? Like, that's a pretty precise limit on an unknown mystery particle. So that's, I think we should give ourselves a pat on the back for that one. And this is the cartoon picture we have of what dark matter would look like if we could see it. So it would be a big puffy cloud of particles, we think, like this, sort of a watermelon in 3D with a little galaxy sitting in the very center. That's the cartoon picture of what we think we would see if we had some dark matter goggles. I'll show you a computer simulation later, which gives you a little bit more of a less cartoony picture. The reason that the dark matter watermelon halo has to be so extended like this is because we know that that rotation curve, that pull of gravity, has to extend out far from the center of the galaxies. So we know that this dark matter must be adding to the gravity far away from the spiral arms of the galaxy. So that gives you a kind of a qualitative idea of why that dark matter cloud, which I'm going to call a halo, it's called a halo, is so extended. And there's a lot of different theoretical dark matter candidates out there. Here are just some of the names. The names that you've probably, if you've heard of any of them, you've probably heard of WIMPs, weakly interacting massive particles. Yeah, there's also machos. Some people came up with. I didn't list it here. Actually, that would go in this category. So WIMPs and machos, but sterile neutrinos, axions, primordial black holes. The key here is that each one of these many different whole zoo of candidates would solve some additional big open question we have in the standard model. So I've highlighted one, which is where is all this gravity coming from? But it turns out there's a bunch of open questions we have just about particle physics that don't fit in right now to the standard model. So it'd be really nice if you could just solve two birds with one stone, figure out where neutrinos get their mass and have a sterile neutrino dark matter. It would be great. A lot of people would be happy. It would be efficient too. So this is, I think I just want to really tie home to you that even though we're observing this extra gravitational force on these galactic scales, these are all going to come back down to some really fundamental particle physics, like little particles that we could maybe detect with something like the Large Hadron Collider, or that is affecting early universe physics. So how do we learn more about dark matter? So you're going to have to come with me on my journey through some more dark matter facts before we can get to how I'm going to learn about dark matter with my research. So this is the computer simulation I said you would show. This is what, if we could put on our dark matter goggles, like put it on the Hubble Space Telescope, look at the universe, this is what we would see, we think, if our whole thing is correct. So we would see this big web of dark matter. And then at the junctions, if we were to zoom in, we would see that watermelon-shaped halo I was showing you before, and the galaxy sitting in the middle with gas and stars. So what you see in addition to this big, smooth, dark matter structure is these little clumps of structure here, right? We're calling those subhalos. Those are small dark matter halos gravitationally bound to the main halo. Here's the key point for my research. So the number of those small structures, those small dark matter structures, depends on the particle physics. I listed all those different particle models. I didn't explain them. You had to just believe me. But what is important for us today is that something like a weakly interacting massive particle, dark matter particle, predicts a lot of small, clumpy structure, whereas a different alternate model, this sterile neutrino model, predicts much smoother structure on small scales. And again, this bar here is showing a size scale about 100 times the size of the Milky Way. And these are, again, just simulations of dark matter structure in the universe with two different kinds of potential dark matter. So if I could just put on goggles, dark matter goggles, I would just look and see, okay, it's a cold dark matter universe, it's a weakly interacting massive particle universe, or it's a smooth universe, it must be more like the sterile neutrino. And from that I would say, oh my goodness, sterile neutrinos, I've also solved this standard model physics problem at the same time, and it would be great. And some dark matter models, and actually just even this main WIMP dark matter particle, and I did a bad job here. So cold dark matter is a generic term for the WIMP dark matter. So I apologize for that. But this model is actually kind of our baseline dark matter model, this cold dark matter model. It's simple to simulate, it matches a lot of observations, and it has some nice properties when you theoretically predict the abundance of dark matter. So this model, if you assume every one of these little halos that's orbiting around the big halo has a galaxy in it, it would predict thousands more small galaxies than what we actually see when we look at the small galaxies around our Milky Way. So this theory would predict there would be a large number of halos then without any galaxies in them at all. So just self-gravitating dark matter structures that don't have any galaxies. So that's a pretty interesting prediction. That would be pretty cool to detect. But the point of that is that you can't just look at the number of galaxies to see how much small self-gravitating structure there is and test these different theories. That's not going to work, because it could be that you have a self-gravitating structure that just doesn't have a galaxy in it. So you need another way to count the number of these small galaxies so you can test which dark matter model is a better representation of what you see. So we want to measure how many of these small dark matter halos there are, and then see if there are any completely dark halos. And for that, we're going to use the James Webb Space Telescope of strong gravitational lenses to test these dark matter models. So here are some gravitational lenses. These are real pictures. These are actually taken with the Hubble Space Telescope of some gravitational lenses. And we're going to sidetrack. We talked about structure. We now understand kind of the basic premise of what we want to do, but I'm going to have to tell you a little bit about the tool we're going to use to do this experiment, and that's this gravitational lensing. So that's this little detour we're going to do right now. So gravity pulls on light too. It doesn't just pull on particles, it pulls on light. This is light coming from the actual star, but then it gets bent as it travels around the massive object, and we think we're seeing it here. So what we see is the light getting deflected. This was one of the fundamental ways in which Einstein's theory of general relativity was proven to be true. And this is I don't remember what the word is, but when they make a photo look nicer, an old photo restored, I don't remember. But you can see here, so this is the original position. This is where the star would have been. Okay, sorry, back up. Solar eclipse, this is a solar eclipse. This is a photograph they took of the solar eclipse. So normally, if you look at the positions, you have a star here, a star here, a star here. You know how far they should be from each other very precisely. Every night you look up, it's the same thing, pretty much. But then the sun comes in front. The sun is a massive thing. Now, normally, we can't see a star close to the sun because the sun is bright. But with the solar eclipse, suddenly we can see the stars close to the sun, and we can see that this thing has been deflected significantly from where it normally is, and that's just because of the gravitational effect of the sun. And so this was it. And the amount of that deflection was definitive proof of this theory of general relativity. It's beautiful. A beautiful experiment, a beautiful prediction. And then I love this newspaper headline. It's so good. Lights all askew in the heavens, men of science more or less agog over the results of eclipse observations. Einstein theory triumphs, stars not where they seemed or were calculated to be, but nobody need worry. Book for 12 wise men, which is some reference that I don't, maybe if anyone knows what that's referring to. No more in all the world could comprehend it, said Einstein when his daring publishers accepted it. I was like, I don't know if this was like normal then. There's like 30 different headlines here. They were so excited about it. But that was great. They should be excited because this is a beautiful thing. And I think we all just think of I don't know, I think this is one of my favorite fun facts though, when people are like, why are you doing your job? Well, mostly because I think it's cool, but I like to throw this out there so it seems a little bit less selfish. Knowing gravity bends light is essential for things like GPS. It would not work correctly if we did not have general relativity. So, you never know when your theory or your measurement or the thing you're working on is going to become super important in the future. And understanding the universe is an important thing. All right. So GPS is great, but we can also learn about dark matter, so let's continue. So if everything's aligned correctly, you don't just get a deflection like what we were seeing in the other thing. You can actually also see multiple copies of the same image. So here's another cartoon, and instead of just the one deflection, we actually see two copies, and you can reproduce this yourself when you get home with a wine glass. So you have some kind of a small point of light. If you hold the wine glass stem up like this, you can get 3 images of the light, 1 ring like this, or 2 images and a little image in the middle. Now, what's happening with the glass is obviously physically quite different in terms of why the light is being bent, right? In the glass, the light is interacting with the material, and that's causing that. In gravitational lensing, everything can happen in a vacuum. It's literally just because that space-time is getting distorted by the massive object. But optically, the calculations are very similar, and you can really, this is a nice representation of this. And so here, if we look down here, this is what I see in real life with the Hubble Space Telescope when I look at a gravitational lens. I have 4 copies of the same bright background light source and a little galaxy that's a lot closer to me that's causing those 4 images to appear. And let me see if I have, I don't think I have the wine glass again, so I'll just show it one more time. So 1, 2, 3, 4 is back there. So that would be the equivalent of what I'm looking at. And then the cartoon, I have a background source here, in this case, a shape, and then I have 2 copies of it here. So we're just seeing 2 of the 4 copies. And what's causing the lensing instead of a star in the other pictures I was showing you before is now a whole galaxy with its own dark matter halo. So I have my main lens galaxy in a dark matter halo. And what's really important here is the 4 image positions and their brightnesses are sensitive to small dark matter structure. So every light ray, as it travels from that background source to me and gets gravitationally lensed, is tracing the dark matter all along the path from the source to me. And here's a real example of this gravitational lensing. So on the left, we have an observed lens. This is, again, we see that same pattern with the 4 images of the background light source. And then in this case, this brown shape in the middle is a galaxy that's closer to me. I can do a calculation of what I expect that pattern of images to look like based on what I know about galaxies and their dark matter halos, or what I believe to be true based on my theoretical simulations. And I get this configuration here. So I can match those image positions really well, arbitrarily well. However, this image here, you can see, has been really demagnified compared to my theoretical prediction. This theoretical prediction did not have any small-scale structure in it. So what's happening is that a small-scale structure near this image, and I am leaving out a lot of details that go into how we check everything, but this is the big picture. A small dark matter structure near this image is causing this to be demagnified. Somewhere along the line of sight from our source, light source, to us, we're getting a little dark matter halo that's affecting how that light travels to us and is changing its magnification. So statistically, we can look at a lot of gravitational lenses, look at how frequently we see a pattern that's different from our theoretical pattern without small-scale structure, and then statistically infer how much of that small structure there is. So we started this measuring these image brightnesses. Again, there are some extra technical details I haven't gone into, but we started this using Keck on Mauna Kea. So Keck is a sister observatory to Lick Observatory. The University of California has a lot of access to Keck Observatory. And this is some data we got. This is a Hubble Space Telescope image of our gravitational lens here. And then this is our data we got with Keck. So I wanted to highlight this this here. So this is a normal ground-based telescope, quite a large ground-based telescope. I can make my telescope pretty arbitrarily large and it wouldn't look better than this from the ground because the atmosphere has such a strong blurring effect. Once you get to a certain telescope size, you don't gain anything because the atmosphere is blurring your images. You don't gain more resolution. But thanks to something called laser guide star adaptive optics, sorry. Oh, there, okay, good. Which was pioneered here at Lick Observatory. We get this amazing resolution even from the ground. So it's correcting for the ground-based, for the blurring from the atmosphere using a laser. And that was pioneered here on this mountain by many of the people who are helping organize these events. So anyway, I wanted to highlight that because it's amazing what science we're able to do from the ground. And then this is just me there's me on a recent visit to the Keck Observatory. So we did our measurement. We looked at the relative brightnesses of the images, statistically looked at how often we saw a deviation from our theoretical prediction without the clumpy structure to with the clumpy structure. And with those 8 lenses, we were able to rule out dark matter models that looked like this. Dark matter models that were really smooth. We have to have dark matter models that are clumpier. I'll show you this just so you know I'm not just publishing papers that have X's on things. You know, this was our whole scientific results. So it was, at the time though, I'll say, at the time it was one of the strongest constraints that had been made on the clumpiness. And by at the time, I mean like 3 years ago. So this is an active field that we're really working on. And so that was super exciting. This is a really small sample of these lenses. And so how are we going to keep making progress? One of the ways is with the James Webb Space Telescope. So James Webb lets us measure the lensing effect with an even smaller light beam. It lets us detect smaller halos than we could before. And I'm going to get into that just a little bit. Okay, so one of the many details I didn't discuss before was how your sensitivity to a small scale clump depends on the size of your light source. Okay, so there's a lot of things that are going to affect what the lowest mass thing I can detect with my lensing is. One of them is the physical size of the light source. And we can see that here with our dark matter cat. And I actually started using this in scientific talks because it's just a nice visual. Even though we don't think dark matter looks like this, you can see the small cat, the light source is small, the cat affects a lot of the light, right? A larger fraction of the light. And when the light source is large relative to the cat only affects it a little bit. It's a smaller relative change. And you can look at that here. This is the change in the brightness of one of those lensed images I was showing as a function of the distance of a small dark matter clump from the center of that image. All right. The main thing, if you take nothing else, so as I go lower on this plot here, I have a bigger and bigger change in the amount of brightness, a percent change, right? So we expect this cat will have a big percent change on the brightness, and this cat will have a small percent change. And that's what we see here in this simulation we did. The James Webb Space Telescope will let us look at light sources that are 6 times more sensitive to low mass dark matter structures. And the more low mass dark matter structures we can test, the more fine discernment we can get between these different dark matter models. And then to do this measurement, we really need a telescope in space. So now I'm going to talk a little bit about why James Webb needs to be in space for us to do our observations. So as many of us know, almost everything emits light. For instance, if you have an infrared camera and you look at a cat, you will see the cat at about 10 microns. This cat is measured to have a temperature of 87.5 degrees Fahrenheit. I suspect that that's because of the fur and not because it's dead. But even the Earth's atmosphere has some temperature, right? It's not 0 degrees, and so it's also emitting some light. it emits light at around 2 microns, so that's out here on this scale, for whatever that means. And this light source I want to observe here, the fine light source that's really sensitive to low mass dark matter halos, emits light at about 25 microns. So much, much, much longer wavelengths than our Earth's atmosphere is emitting light at. Because of that, and because redder light sources tend to be fainter, and our light sources are far away, and that our atmosphere is super bright at 2 microns, we simply have to do this kind of a measurement in outer space. And so James Webb has other science purposes besides mine, surprisingly, but for all of these science cases where we want to observe out at these kind of really long wavelengths, we need to be in space. Weirdly, though, if you get to long enough wavelengths, you're in the radio, and then you're fine. So it's really, you just have to get away from this region of the spectrum where the atmosphere is super bright. Anyway, that's another story. This was one of my colleagues. Trying to observe in the infrared from the ground is like trying to see stars while your telescope is on fire and the sky is on fire. One of my very frustrated colleagues. So the James Webb Space Telescope is far from the Earth. It's much farther from the Earth than Hubble. It's actually farther from the Earth than the Moon. I made this when I wasn't sure if there would be children in the audience, but I think we can all appreciate that outer space is really high up. 100,000 giraffes I calculated to get to outer space. So we have to launch it in a telescope. This was the launch of the James Webb Space Telescope. And what was really interesting about this rocket and this whole mission is that the telescope itself is wider than the rocket they had to put it in. So it had to unfold, and then the mirrors had to come out here on the side. I don't think this shows that, in order to be able to fit it inside the rocket to launch it all the way out into space. Because James Webb has a giant mirror. It's 21.3 feet in diameter. And we can see what an improvement this makes on our resolution. So here are some space telescopes. This is 4 microns, an image of 4 microns at 8.6 microns, so a similar wavelength range. And you can see this is Spitzer. This is a later infrared telescope. And then we have JWST MIRI, and it's just beautiful, right? I mean, all this detail in the clouds. It's when we were looking at some of the first images we got from James Webb, we were saying it's like opening your eyes. It's like just seeing this whole new vision of the universe. Not only does it have to be all the way out there, but it turns out it also has to be cooled. So it would be heated so much by the sun that it wouldn't be able to do these deep observations. So here is some of my data I took with the James Webb Space Telescope. This is real. This is the previous information we had at these wavelengths about this system, all right? So for my science, I'm measuring the relative brightnesses of these 4 point sources, and I'm gonna just do that experiment I told you about. I'm gonna see whether that configuration looks like it could be matched without a perturbation or whether it needs a perturbation. I don't have an answer for you yet, so don't hold your breath. We're working on it. Hopefully, we expect our first science results to come out within the next couple months, and then our main result from our full survey will be in the spring. But we do think, based on our forecasts, that if those completely dark matter halos exist, we will be able to see them with this measurement that we're doing. So we're very excited. We'll be able to hopefully answer whether there are dark matter halos without any galaxies in them and put new limits on this dark matter. And I wish I could move faster and I could have had the answer for you already, but maybe stay tuned. And then looking further into the future, there's just a lot to be doing with this kind of measurement. So we're going to be discovering a lot of new gravitational lenses in ongoing surveys that are looking for interesting objects in the sky. So we expect thousands within the next 5 years or so. And things like the 30-meter telescope that might be built on Mauna Kea could let us make even more sensitive measurements of the nature of dark matter. And this is just a comparison of the kind of data I was getting from Keck. This is a 900-second exposure. We can see the 3 images here, and then a 10-second exposure with a 30-meter telescope. So the future is really bright. I'm very excited, and hopefully we'll have some press releases or something by the spring with some science results from the James Webb Space Telescope. That is all.
Thank you.
So, yeah.
I have a question for you. What is the estimate of the density of clouds or halos?
Yeah, excellent question. And I'm unfortunately at this moment I don't remember the numbers off the top of my head for like how many particles are passing through us at this time or those kind of numbers. I think, let's see. So okay, I'm going to try and do an estimate. So let's say, I'm going to have to give you a number in like solar masses per kiloparsec, and I don't think that's super useful. So I'm sorry. Let me Google that right after and get back to you. Sorry.
Well, and the reason for the question was, well, what happens if we travel through there with a spaceship? Would we know that?
Yeah, so the idea, if we're all right, is right now there's dark matter in this room, actually. It's just passing through us. And there are other kinds of particles we know that are definitely passing through us. Neutrinos are coming from the sun, from outer space, passing through us all the time. Those we've actually detected. So the theory would be that dark matter also, and I feel terrible that I can't give you that number of particles per second, but it's some number coming through all the time.
But that density would exist around a galaxy, and would there be spaces between blobs of dark matter?
So yeah, you could imagine it like, I think maybe a good visual would be like a pudding. I don't know why that's a good visual, but like you have some denser regions in the pudding. So you're always in the pudding, but sometimes you're in a big clump of pudding. And that would be like the subhalos. But right now we'd be like in a low density pudding area. Yeah.
Why 3? I can imagine why maybe more than 1.
Yeah.
But why 3?
Well, it's actually 4. It's actually 5, actually. Okay, well, we can't see the 5th one. The 5th one is demagnified in the middle. You can't see it.
Why a fixed number?
Yeah, it's if you solve those equations, you get a certain number of solutions, and it's surprisingly rigid in the number of solutions you can get. Yeah, I don't have a more intuitive. It's very straightforward, simple calculation. Yeah, about the number of images you get, and it like if you cross certain infinities in the magnification, then you get more images. So it's all pretty straightforward. Yeah.
With that colder, lumpier model,
Yes.
what are the more likely candidates of that list? Which one?
I think, let's see.
Does it lean into one group more?
People would say I think most theorists would say they think this model is the best model so far.
Can that be the Webb?
Yeah, I don't think we have a good reason to actually make that statement, though. I think mostly it's easier for them to simulate. So I personally don't feel like we have any kind of prior expectation for what it should be.
So you don't have a favorite candidate?
I would love it to be something nobody expects, just to make it more interesting, but that would be my favorite. Yeah.
So with regular matter, we have an entire Mendeleev table of different types, and the quarks, even the quarks are different.
Yeah.
Why do we think that this dark matter is one uniform thing?
I love that question. Just because we're just like, it's a starting point. There's absolutely no reason there shouldn't be a bunch of different dark matter candidates. Absolutely, great question. So we're like, let's try and figure out what the average properties are, which doesn't sound as great as if I tell you I'm finding out what it is. So that's why I say the nature rather than the average properties, but yeah.
the Einstein experiment, they knew the position of the stars when it wasn't an eclipse.
Yes.
Okay, and so I get that. When you take a picture from these telescopes, obviously you just see a bunch of dots of light.
Yeah.
How do you know they're these images and not just a galaxy? How would you differentiate?
Such a good question. Yeah, did everyone hear that question? First of all, how do I even know those are 4 copies of the same thing? So it's with spectroscopy. So we can measure the distances to things by looking at emission lines. Okay. So if we look at the sun, it has different elements in it that get excited, and we can see spectral features. We can see a signature, and I can match that to a distance, a cosmological distance, but for this light source. So I can look at it. There's certain ways we can measure the distances. So I see all 4 things are at the exact same distance. That's actually the only thing you need to know, not the thing about spectroscopy.
So the first thing look similar to each other.
They look exactly the same and different from everything else around us. We have 4 super bright things that are at an identical distance, which we can measure really accurately. Yeah.
The way it's bending when you show your cartoon of the light.
Yeah.
How do you know the path from the north side is the same as the path length on the south side?
They have different path lengths, actually.
Then they would be different distances.
So the physical distance, the light traveled is different. They actually arrive to us at different times. The universe is expanding. So if one thing gets to me a different time, it had to travel a different distance. It's physically at the same location in the universe. I talk about it being at a distance, but I can actually measure the physical location in the universe, and I'm happy to discuss that more, but it has to do with the space-time expansion. So those things are at a location in the universe that is expanding the same rate away from me, all 4 of them. So that's what I actually measure. Yeah.
Thank you.
Uh-huh.
So then that energy also affects that result because affects the actual speed of expansion of the universe.
Yeah, that's right. Yes. So I have to take into account that light had to travel to me, and it got distorted by that travel. Yes. Yes.
As you're running simulations and trying to figure out the positions of the dark matter, you can see spectral lines and you can kind of figure out the physical points of the stars. You have no idea what the dark matter is. You can't see it, right?
Right.
So how do you keep from overfitting and as you're guessing?
Yeah. So the statistical analysis is a really important aspect of this. I certainly can't say there's one dark matter clump here at this location. All I can say is models which have this amount of dark matter do a better job fitting my data. And honestly, with only 8 lenses, we weren't expecting that much of a strong result, but they were perturbed enough that we had to have models that had they produced a lot of clumps, right? So I can't say. So what we do in our analysis is we draw a realization of these small clumps. We look and see if they match the flux ratios, and we do this hundreds of thousands of times. And so maybe 10% of the time one particular model matches our data, and another model matches our data 50% of the time. So we're saying this is more likely to be the correct dark matter model. So that's how we do it.
Generates kind of a possible confirmation of dark matter thing.
Yeah.
And you see, could this confirmation have generated this picture?
That's exactly what we do. Yes. Approximate Bayesian computing, if you're interested. Yes.
Wait, this might be a bad question, but how do we know that gravity is different from dark matter? Like, what if the dark matter models that you showed is gravity? You've got our knowledge of gravity.
That is not a bad question. That is a great question. And it could be, so far no one has come up with a way to modify gravity that matches all the things I talked about. So some people have modified gravity so that it can match that spiral arm structure that I showed. There is a way to do that. But if you take that model then and try and match the way those galaxies are orbiting around each other, it doesn't work. That's not to say someone might not find a solution that does that. But so far, nobody's managed to come up with something that works at all those different scales: cosmic microwave background, galaxy cluster, and us. Yeah.
So for the cosmic microwave background, I know it's like light that's present.
Yeah.
So if dark matter doesn't interact with light, how does that cause the fluctuation?
It interacts gravitationally with the light, and distorts the cosmic microwave background compared to what we would expect. So it's that gravitational interaction that we're seeing, yeah. Those are great questions. Yeah.
So from the list of things that we know about, we conjecture we know about dark matter in the beginning, so that basically only has a gravitational effect that we can see, measure, or observe.
Yes.
It doesn't interact with light in any way that we can directly see.
Right.
But it interacts with itself gravitationally.
Yes. Yes. Yeah.
So we could have dark matter, potential rotations, galaxies, etc. But how, because in order to see something, it has to emit light in the universe, so stars, we can see them, or, I don't know.
Right, yeah.
We cannot see dark matter, but we can also not see regular inert matter unless it's illuminated by light.
Yeah.
There's a lot of vast distances in space without any stars.
Yes.
Why could we not explain away regular matter what we're seeing?
Yeah.
We have to give it that dark matter label.
That's a great question. So it's like, why isn't it just some kind of particle, like maybe neutrinos, for example? Neutrinos we know don't interact with light. So why can't dark matter be neutrinos? Well, I mean, neutrinos in particular are ruled out because of other considerations. But some of that, you can do some really nice calculations based on things like the cosmic microwave background, which put pretty strict limits on how much standard model matter there is. And so that's where we're kind of getting some of those calculations about how much normal matter there is compared to the dark, whatever this dark matter is. A lot of it comes from those early universe physics calculations.
So it interacts gravitationally with itself and with other matter differently than regular matter interacts with itself?
It interacts gravitationally, supposedly, the same with everything. Itself, other matter, space-time, it all is the same. That gravitational interaction is the same. So basically, to match the cosmic microwave background, you need some things that are interacting electromagnetically to get, and I can't really fully explain it in the amount of time we have, or / with the background knowledge, without a bunch of extra background knowledge. But this shape with these peaks here. So basically, and this is just a description of like if you see one clump, how likely are you to see another clump? So how correlated? Yeah. So these peaks we see in the spectrum really have to be matched by a combination of two kinds of things. One is one is a particle that doesn't interact with light, and one is a particle that does interact with light. And you need those two to get the dotted line shape. If you don't have the dotted line shape, if you don't have the dark matter, you get this blue curve, and it really deviates from what we see significantly. And actually, this prediction was made by someone who investigates alternate theories to explain. He investigates this modified Newtonian gravity. So he's saying in this paper, like, I can't explain this with my current model. Anyway, the point is you need those two things. So then you could say maybe neutrinos. The problem is neutrinos are too low mass. And so we really don't have a standard model particle that will do this. Yeah.
Is dark matter related to the expansion of the universe?
So it could be connected in some way. Nobody's come up with a nice self-contained theory that would make that work, but in principle it could be. On the other hand, it could be just completely unrelated, and I think maybe that's the case. Certainly in like the WIMP model, the standard model we think about, they're totally unrelated.
But wouldn't you explain why the universe is not just faster?
It does, yes, sorry. In the sense of if you want to understand the evolution of the universe over cosmic timescales, then you do need that dark matter, right, in your model to understand that. But it doesn't explain why it's accelerating apart. Like, that doesn't give you the why for that. Yeah, right. You need a certain amount of energy density and matter. And yes, that's right.